In this lecture, we're going to look at the Upwind method and the dissipation that introduces and try to understand that a bit better, along with another first-order accurate method that's also quite dissipative called Lax-Friedrichs, and then look at some second-order accurate methods, the Lax-Wendroff and Beam-Warming methods, and see how they give dispersion rather than dissipation as the dominant error, and then look at the idea of a modified equation as a way to better understand what's going on with these finite difference or finite volume type methods. So let's also take a look at this symmetric method in which we've used a centered difference, qi plus 1 minus qi minus 1 divided by 2 delta x as an approximation to the derivative of q. Or another way to look at that is that this is a method in flux differencing form, but where we've defined a numerical flux based on two states to be the average of the flux to the left and the flux to the right. I mentioned this before, I believe, as giving us a method that seems quite natural and yet is unstable in practice. If you try to use this method and you fix delta t over delta x, or you fix the Courant number and you refine the grid, then even though it's order delta x squared approximation to the derivative that's being used, which seems better than an Upwind method, for example, it turns out it's unstable and it doesn't converge unless you let delta t go to 0 faster than delta x. But there's a variant of this that can be used, which arises from taking the qin here and replacing it by the average of qi minus 1 and qi plus 1 at n. So if you make that change and leave the sort of flux differencing term or the approximation to a dq dx alone, then you end up with a method which is actually stable provided the CFL condition is satisfied. For each eigenvalue, you need lambda times delta t over delta x less than or equal to 1. But if that's satisfied, then this Lax-Friedrichs method is stable. It's still only first-order accurate, it turns out. We're still doing a sort of first-order updating in time, even though we have a second-order approximation to the spatial derivative. And you can also look at it in the following way. If we just rewrite this term a little bit and combine it with this term, you can pull out a qin and have a centered difference of aqx. I guess it's actually this term, this first term that we're splitting up into qin, and then what's left over we can look at as 1/2 qi minus 1 minus 2 qi plus 1. So these two terms are the same, but the qin and this term combine to give you the averaging of q in the Lax-Friedrichs method. If we rewrite that a little bit more, we can write it in this form, just introducing some more factors of delta x and delta t so that it looks like approximations of first and second order derivatives in x. And so what we can see if we write it this way is that we have here the unstable method that I talked about on the previous slide, where we just take qin and update it by the centered difference, plus an additional term that comes from this change in the Lax-Friedrichs method. But by rewriting it this way, we can view this additional term as an approximation to the second derivative of q in x times a coefficient times delta t. And so we can look at this as sort of approximating the advection equation, but with an additional term, some epsilon qxx involving the second derivative of x, where the epsilon is equal to delta x squared over 2 delta t. And so if we look at it this way, we can view this as really we're approximating the solution of this parabolic equation, which has smoother solutions than the hyperbolic equation. And if we start with, say, a step function for this advection diffusion equation, then we know that that step will smear out as it moves. And that's exactly what happens when we use the Lax-Friedrichs method or also the Upwind method. What we find numerically is that it's really looking more like a solution of this advection diffusion equation rather than a solution of the original advection equation. But the epsilon that we've introduced here is delta x squared over 2 delta t. So if we fix delta t over delta x and refine the grid, that vanishes. It goes like order delta x to 0. So we've put in a little bit of extra dissipation, but with a coefficient that vanishes as we refine the grid. So in the limit, it vanishes as we refine the grid. The results get sharper. And so this is the idea of using an artificial viscosity or a vanishing viscosity as we refine the grid. And even though it's a parabolic problem, so you might think based on what we talked about regarding the stencil needed for solving parabolic equations, we can get by with using an explicit method, even with delta t over delta x fixed, because of the fact that this coefficient in the parabolic term, the epsilon, is vanishing as delta x goes to 0. And it turns out that's enough to sort of restore stability for these explicit methods, whereas if you fixed epsilon as delta t over delta x goes to 0, then it would not be stable unless you refine faster in time than in space or used an implicit method. We can do a similar sort of analysis on the Upwind method. If we go back to the original Upwind method for advection with U positive, so that we're looking to the left in our advection equation, then this gives a first order accurate approximation of the advection equation. If we compute the local truncation error, we find that it's first order accurate. And if you remember the analysis of computing that local truncation error, there was a leading term in the truncation error when we did Taylor series expansions of qi minus 1 about the point xi and qi at time n plus 1 about time tn. When we did those Taylor series expansions and combined things, there was a zero order term that was exactly qt plus uqx. And then because we had plugged the true solution in, we could say that's 0, and that dropped out, and we were left with an error that was delta x. But suppose instead of trying to approximate that equation, suppose we were trying to approximate this PDE here instead. And so if we said Q is really the exact solution of this equation, and we did the same Taylor series expansions in the Upwind method, but then assumed that this equation, this differential equation here held for Q, then more terms would cancel out, and the local truncation error would turn out to be second order delta x squared and delta t squared accurate, rather than only first order accurate. So we can view this Upwind method as being a first order accurate approximation to the original advection equation, but it also gives a second order accurate approximation to this advection diffusion equation. And so again, we've got a diffusion term here that the 1 minus u delta t over delta x is constant if we fix the Courant number as we refine the grid, but there's another coefficient out in front that involves delta x. And so again, this viscosity in the advection diffusion equation, or the diffusive term, is going to 0 as we refine the grid. So it's a slightly different term than comes out in Lax-Friedrichs, but similar sort of interpretation. So again, this equation, this type of equation, is what's called a modified equation. It's a way of sort of modifying the original differential equation to give a differential equation that better models the behavior of the numerical approximation. So we started out by having a partial differential equation and developing a numerical method that models the differential equation, hopefully. Now we're kind of turning that around, and we're saying, given this numerical method, find a PDE that models the behavior of the difference equation. And since we know that an advection diffusion equation tends to smear things out, that tells us that we can expect the Upwind method, the dominant error in the Upwind method, is going to be in the form of things being smeared out as they propagate. Oh yeah, you can also note from this that if we happen to choose the Courant number equal to 1, then we've seen before that this Upwind method reduces to sort of the exact solution. QIm plus 1 is QI minus 1n. And if Courant number is exactly 1, then this term is 0, and so we actually have a second order approximation to this equation with no diffusion. Of course, there's still potentially higher order terms, but in fact, for this particular case, all the higher order terms also drop out, and we end up with an exact solution of the original equation. So here's, again, an example of just solving the advection equation with the Upwind method on a unit interval with periodic boundary conditions. So the solution should just wrap around, and at time 1 it should agree with the initial data. If we take 200 cells and use the Upwind method, then we get quite a bit of smearing of the discontinuities, and we also lose the peak and this smooth Gaussian. If we refine the grid and use 400 cells, then we get better resolution, which we can now interpret as we're solving an advection diffusion equation with a diffusion coefficient that's only half as large, and so things look better as a result of that. But if we want to make things look even better, we might want to use a second order accurate method rather than only a first order accurate method. And so one standard second order method for linear hyperbolic equations is the Lax-Wendroff method. And it's based on this Taylor series expansion for q at time t plus delta t is q at time t plus delta t times the time derivative. And for the first order method, like Upwind, we simply replaced the qt with minus uqx and then use some difference approximation to the qx term. But if we also include this next term in the Taylor series and insert also a difference approximation to that second derivative in time, then we can get a higher order accurate method. Of course, since we're trying to base this on a single time level and step forward in time, rather than having higher order derivatives in time, it's more convenient to have higher order derivatives in space. But we can use our original differential equation if we're looking at the linear system qt plus aqx equals 0, that differential equation, if we differentiate with respect to t and also differentiate with respect to x and eliminate the cross derivative qxt term, then we find that the second derivative is a squared times qxx. And so we use that in looking at the local truncation error of the Upwind method, but now rather than doing that, we're going to use it to actually come up with a better approximation to the solution of the differential equation. So the qt term we can replace by minus a times qx. The qtt term we can replace by a squared times qxx. And so we get this expression for the exact solution at time tn plus 1 as a Taylor series, but now where we've got spatial derivatives in it. And then if we replace each of the q's with the corresponding numerical approximation, and if we replace this first order term by a centered difference, exactly the same centered difference we looked at before that was unstable, qi plus 1 minus qi over 2 delta t, but also add in an approximation to this qxx, that's the second difference divided by delta x squared, then we come up with what's called the Lax-Wendroff method. And you might say, well, this looks very much like the Lax-Friedrichs method. We manipulated Lax-Friedrichs so it had exactly the same sort of form. It looked like this unstable centered method plus some coefficient times this second difference. And it does have exactly the same form as Lax-Friedrichs, but if you go back and look, this coefficient that sits in front of the a squared term is different here than it was in the case of Lax-Friedrichs, and it still has the same sort of stabilizing effect that it gives us a method that's stable up to Courant number 1, but now we've chosen this coefficient in front of a squared to be the optimal coefficient so that the diffusive term and the truncation error actually cancels out completely, and we get one higher order of accuracy. Again, we can think about this in terms of a modified equation. We could do exactly the same thing we did for the Upwind method, derive the local truncation error by replacing the capital Q by little q, the solution of the original differential equation. And if you take as your differential equation that we're trying to solve the advection equation, as we normally do, then if you do that, what you'll find is that the local truncation error for this Lax-Wendroff method will be order delta x squared and order delta t squared. It will be a second order accurate method. But if instead we suppose that we're trying to solve this equation and that Q is the exact solution of that equation, and we plug that in and go through the local truncation error analysis, then another term drops out and we get a method that's actually third order accurate. So the Lax-Wendroff method, although it's second order accurate on the equation we're really trying to solve, it's third order accurate on this more complicated equation. And therefore we can again sort of turn things around and say, well, this differential equation here gives us a model for how the Lax-Wendroff method behaves in practice. So if we can understand how solutions of this equation behave, then that will give us some insight into how numerical solutions computed with Lax-Wendroff behave. And now this equation, we have again the advection equation, qt plus uqx equals, but now instead of 0, we have some coefficient times a third derivative of x. So it's no longer a diffusive term, and this isn't a parabolic equation the way the advection diffusion equation is. Instead, the third order derivative gives a dispersive term, as it's called, and we'll talk in a minute about what that means exactly. But it gives some dispersive term, and again it has a coefficient that's some constant based on the Courant number, but then out in front of that there's a delta x squared. So again this coefficient vanishes as we refine the grid and we get closer and closer to solutions of the advection equation. But for any finite grid, it gives us, if we understand the behavior of this dispersive equation, it gives us a better idea of how Lax-Wendroff behaves. Now the idea of dispersion, the reason it's called dispersion is because if you do a Fourier analysis, if you assume that your data is a linear combination of Fourier modes with different wave numbers, then if we were just solving the advection equation, all of those different wave mode numbers would travel at exactly the same speed. There's only one speed involved, the advection velocity. Any initial data travels with that velocity. A high frequency wave or a low frequency wave both travel with the same velocity. But once you add in a dispersive term, or a third derivative term in this case like this, then it turns out that different wave numbers travel at different speeds. So waves disperse, the different frequencies or different wave numbers disperse. And that often shows up as solutions becoming oscillatory, particularly if you start with step function initial data, because a step function has a lot of high frequencies in it. If you do a Fourier decomposition, the Fourier transform decays very slowly, and you need a lot of high frequency information to represent a discontinuity well. And those high frequencies are moving at different speeds than the lower frequencies, and they separate out, and you see that most clearly around a discontinuity. So to kind of understand that a little bit better, here's just a brief summary of how you do the sort of Fourier analysis. And you would, in general, think of decomposing your data as a linear combination of Fourier modes, or taking a Fourier series or a Fourier integral, depending on whether you're on the finite domain or the infinite domain. But for this sort of analysis, it's enough to maybe consider a single Fourier mode. So it's supposed that our initial data is of the form e to the I cx for some wave number xc, and that the solution has the form e to the I times cx minus omega t for some omega. And for linear differential equations of the sort we've been looking at, it turns out that the solution does have this form for this particular kind of initial data, and that's why you can use Fourier series to represent the solution in general. So based on the particular PDE, we get a different relation between what omega has to be and what wave number xc we started out with. Omega is like frequency in time, xc is like a wave number in space. And that relation is what's called the dispersion relation for the PDE. So if we're looking at just the advection equation, then we need to, so we're looking at qt plus uqx equals 0, for example, then if we assume this form of the solution up at the top, then we can compute qt as minus I omega times q, because when we differentiate this exponential, we bring down an minus I omega if we differentiate with respect to t. If we differentiate with respect to x, then instead we pull down I times c. So if we plug those into this advection equation, then what we end up with is minus I omega q plus u times I c q equals 0. So if we solve for omega, we end up with omega is just u times c. And if we put that back up into this general solution here, we end up with this general form for the solution of the advection equation for a single Fourier mode. Q of xt is e to the ic times x minus ut, which is exactly equal to the initial condition at x minus ut. Sorry, running out of space here, but it's exactly the translating solution that we expect for the advection equation. So this is another way of deriving the exact solution of the advection equation. Not terribly interesting so far. But now let's suppose that we look at an advection diffusion equation where we add in an epsilon qxx term here. Then to analyze the dispersion relation here, we also need the qxx derivative, which we can calculate again by differentiating the exponential twice with respect to x each time we pull down an ic, so we end up with minus c squared times q. And if you combine that with the qt and qx terms in this differential equation and solve for omega and then put that into the general solution for q, what you find is that you have, because of the fact that qxx is real, whereas qt and qx both have this factor of I in front of them, when you plug it in to the solution for q, you end up with a term that looks like exponential decay in time in addition to this translation in space. So this shows us that the exact solution of this advection diffusion equation looks like a translating wave, just like in advection, but it also decays, and it decays at a rate that depends on the wave number. A highly oscillatory wave decays much more quickly than a wave with smaller wave number and longer wavelength, which would decay much more slowly. So that's how the solution of the advection diffusion equation behaves. And then finally, if we look at the dispersive term, if we start with the dispersive equation, like down here at the bottom, then we also need this third derivative of q with respect to x. Differentiating this exponential again with respect to x, we bring down another ic, so we get minus ic cubed times q. And now this again has the factor of I. So all of these terms have the factor of I, and when we solve for omega, we end up with a solution here that is simply translating again, as in the case of the advection equation, but now the speed at which it's translating is not just the speed u as it was here in the advection equation. Instead, it's u plus beta times c squared. So this quantity here, u plus beta c squared, is the speed at which this wave is translating. And so the solution at time t is just the initial data translated by that speed times whatever elapsed time. And so it's like the solution of the advection equation, and if we started with a single Fourier mode, it would simply look like it's advecting along at that speed. But notice that the speed now depends on the wave number, and so different waves propagate at different speeds, and you get this dispersive effect. So if we do the same experiment we've looked at before with the advection equation, but using now the Lax-Wendroff method, then what happens is that after it's revolved once around this interval and come back to where it should be agreeing with the initial data, because of this dispersion, we get these dispersive ripples that appear around the discontinuities. And these are an artifact that come exactly from the fact that these discontinuities, when we do the Fourier transform, have lots of very high wave number information in them. And since those high frequency waves are traveling at different speeds, they sort of separate out, and you end up, the effect of that is that you see these oscillatory ripples appearing around the discontinuity, similar to the Gibbs effect, if you're familiar with that, when you just try to represent a discontinuity with a Fourier series and you don't take enough terms, for example. So we definitely have some problems around discontinuities. On the other hand, with Lax-Wendroff, we're getting much better accuracy in the smooth part of the solution. It's capturing this hump quite well compared to what we were seeing with the Upwind method, for example, where on this grid with 200 cells, there was a noticeable gap there, and even with 400 cells, it wasn't much better. So now you might also ask, what happens to these ripples if we go from 200 cells to 400 cells? Do they get much better? And the answer is, well, they get more concentrated around the discontinuity, but they don't decrease in amplitude. They stay pretty much the same size and amplitude. So as we refine the grid, again, we would not have convergence in the max norm or the pointwise norm. Of course, you don't expect that in general around the discontinuity, but moreover, even a little bit behind the discontinuity, we're seeing these ripples that have finite magnitude and don't disappear in the limit. So those are kind of ugly. They can also be a real problem in certain applications. In nonlinear problems, when you have values that go way outside the bounds of your original data, things may be less stable. In a problem where this might represent, say, the depth of water in the shallow water equations or the pressure in a gas, those are supposed to remain positive, or the problem doesn't even make physical sense. And where we have undershoots like we have down here, well, in this case, this is just some advected quantity Q, but even in the advection equation, Q might represent the concentration of some chemical that's being transported down the pipe, and that concentration physically should always be greater than or equal to 0. So it doesn't make sense to have a concentration of negative 0.2. In the advection equation, it doesn't cause any problem mathematically, but in the gas dynamics, if you have a density of negative 0.2 or a negative pressure, then typically everything breaks down and your Riemann problems don't have solutions anymore and bad things happen. So we'd really like to avoid those if possible. And in the next lecture, we'll look at sort of ways of avoiding that. But I wanted to also mention the beam-warming method, which is just another second-order accurate method that's, again, based on the same Taylor series expansion, but it uses a different approximation of QX and QXX. Rather than using centered approximations, it uses one-sided approximations of each of them, but one-sided approximations that are still second-order accurate. So it still has a second-order accuracy, but it uses a one-sided approximation of the first derivative and a one-sided approximation of the second derivative. So instead of using qi minus 1 and qi plus 1, it's using qi minus 2. So this method has a stencil that looks like this. It would be using 2 points to the left and no points to the right. Turns out you can show that, well, for this method, the CFL condition would be that lambda has to, or this should be not lambda, but lambda times delta t over delta x. This should really be the Courant number in here. Lambda p delta t over delta x has to be between 0 and 2 for all of the eigenvalues, just based on the stencil that we looked at a moment ago. You can also show using von Neumann analysis that that is in fact the stability limit, that if the CFL condition is satisfied, then the method is in fact stable as delta t goes to 0. Von Neumann analysis, by the way, is just doing the same sort of Fourier analysis we looked at for the PDE, but applying it to the finite difference equation and seeing how different wave numbers behave. So if we use the beam-warming method instead of Lax-Wendroff, we might hope maybe that works better because we're using an upwind method, and if we're looking at advection going to the right, maybe it's better to use this one-sided method rather than the centered method of Lax-Wendroff. But it turns out that it doesn't really do any better. It looks somewhat different. If you remember Lax-Wendroff, the oscillations were trailing behind the discontinuity as it propagates. Things are propagating to the right here since the advection velocity is 1. Now in the case of beam-warming, the oscillations propagate in such a way that they show up in front of the discontinuity instead of behind it, and also in front of the second discontinuity that's moving along behind it. We get similar good accuracy in the smooth solution, but we have oscillatory results again for near the discontinuity. And on a finer grid, again, those oscillations do not get any smaller in magnitude. Okay, so the next thing we'd like to look at, we'll go on to in the next lecture, is how to improve the situation and ideally come up with some methods that do a good job of capturing smooth solutions, but also do a much better job than either of these methods at modeling discontinuities.